such a long time since I last posted any video. And the reason being, besides other things, that I was lost in a hard coding challenge, an attempt to code a Julia fractal on the petty Amstrad CPC 8-bit computer, which ended up in one of my proudest optimizations. It was totally random. I wasn't motivated to work on any other project, and that's why I was lost a bit from everything. So I decided one day to do some exploration of high-end algorithms for low-end computers as a pure sport. And then I dived in for I think 2 weeks or more, and I ended up with an actual real-time effect that I have released in a recent CPC intro. While previously when I started I thought this is never gonna be real-time, this is going to be slideshow. And yet I pushed hard, as I always do. I started from slideshow, but then I started improving with, 1 frame per second or 2 frames per second, and then ideas kept popping up. And I started prototyping this in C language using SDCC, the Small Device C compiler, so that I can see it working in a 32x32 resolution. Then gradually improving and started replacing all the real-time multiplication with lookup tables to pre-calculate as much as possible, and it was still slow, of course, in C. And then I rewrote the whole thing in Z80 assembly, and yet it was a bit better, but still not there. So there were still many steps ahead of improvement. There were so many things, every day a new idea. I started having fits of eureka moments. I started walking alone in my room and be like, oh no, if I move this and do that and save this lookup table like this, no, it can't be. I had things like that, and since I'm alone at my home I can scream, it doesn't matter. So eventually it was so good at that point and there were so many ideas, both in low level assembly and high level algorithmic, that during the middle of this adventure I started thinking, hey, if I ever finish this, it's actually a great subject for an episode of Optimosophy, because it's everything there. There are so many good ideas, so many different perspectives of how to optimize an unorthodox way of thinking, and just so good. That effect touches every aspect of optimization, from high level to low level assembly, even fighting to fit the algorithm in a very small 8-bit range of numbers, because usually those algorithms, even if you write them in fixed point, which of course that's what I did, the numbers explode so fast that you might have to go to 16-bit or even 32-bit, but somehow with various tricks I fit them in 8-bit range of numbers. And even storing my pre-calculated tables in such an unorthodox way around in memory, with overflowing regions on the other side of the memory. And then more. There are things unlike anything I've done before, and all the combination of these ideas through, I think, 2 weeks of research had led me from something that started from a slideshow to a bigger effect that would run at 10 to 12 frames per second with 10 iterations of 10 Julia fractal iterations. And there are so many good ideas to present here, a lot of them gradually introduced to the code, so many different approaches one can take, different ways of thinking, things that might open your mind of what's possible, and it might even give you some ideas of, if you are stuck, you are not in this mindset, you're like, I did everything and the thing is still slow, I don't know what to do anymore. You might get some new perspective of different ways of thinking around the same problems. That's why this is such a great episode for Optimosophy. And I hope to present it in a relatively short way, because there are so many things that it could be bigger than I would like to. And after this adventure, this made me wonder about some things. Like, one thing is how much can be achieved with the very simple Z80 processor. How much more powerful I thought the Z80 was. Um, if you really push it and you know how to use it, and you also have this low level and high level optimization concepts and unorthodox ideas, and put everything together, and how even advanced things that would normally need a higher number precision are possible to fit in just 8 bits. And then the other thing I was thinking, what are the limits that are not yet reached in 8-bit platform, let alone 16 bits or later? What are the limits that are not reached in demo scene? Today I have seen so much stuff that it's too rare. It's too rare to see a new effect and say, how is this possible? You know, it's so rare. I might see an amazing effect and think, oh, that's great, but I know how it's done. I know this is possible. I could have done it myself if I wasn't lazy. Okay, it's much rarer today because I know more. I know more about the platform. I know more about the tricks. It's when I started in the demos in that. It's when you are a young child and everything is new. That's one concept, and everything is dreamy and amazing. But when you grow up and you start learning the tricks, it's not as spectacular. There are some cool stuff you can do with old platform, but it won't have the same impact. You know, that's the other thing I was thinking. And even now, my Julia fractal, I might have said, "Whoa, it's amazing that this is even," but now it seems trivial to me. Okay, because I did it, and I don't know if someone else did it on the Amstrad CPC and I would see it. I don't know how I would react. And I don't know if the effect on the intro, because I messed up with some of my movement and it seems very repeated. I don't know if it has the impact that I was imagining. And regardless, you know, that dream of the impossible, there is always that yearning for the dream, and that's what at the end matters. So before I get into details on how I optimize this for 8 bits, I need to start from the beginning and make a brief explanation of the Julia morpher fractal algorithm. Very briefly, just to have a start point, because you know the start point isn't even the original algorithm with floating point, which I represented here in with a shader in GLSL sandbox, and this is full in floating point. It tries to keep the ranges of the pixel and the offset in -1 to +1, although I later multiply some position with 4, because if you go with 1 you are a bit too close. But I generally try to keep it on the small range, and that was the magic with floating point when they were ranging from -1 to 1. If you multiply two floats that are inside this range, they will return you something that is inside this range. But that's not even the start of this whole adventure, because I have done this effect previously in the GP32, and I have kept the moment. And that was pure integer with fixed point, and you have to be careful of the ranges there. That was a gamepack GP32 running at 100 MHz ARM processor, although I think this demo was overclocked at 133. Was doing from, I don't know, 30 to 60 frames per second, I think. maybe even less when there are many iterations. And this was using 16 iteration, it's the same as here. And all I want to say is that when I started optimizing the effect for the Amstrad CPC, it started from the fixed point integer code from this one, because I would never even going to try with floats. So very briefly, if you try to keep the range of your position, so up here is -1, +1, +1, and so on. So I keep it in the range of -1, +1, which might be a lie because I multiply it by 4 to zoom out. But I generally keep the number small because it's with floats it's better. If you multiply the numbers, they don't exceed too much. But if you go with fixed point integer, you have to be careful. So let's explain what's going on. There is several iterations per pixel. X0 and Y0 is taken from the original pixel position. Here is 0, here is minus. It would be -4 since I multiply, and +4, and -4 and +4. So you calculate x1, multiply x0 by itself, minus y0 multiplied by itself, plus offset x. Now the offset is it's based on the mouse position, and it's also in a +1 and -1. I mean, the result will still exceed the range, but might be saved later. I don't know. But because the numbers are small, it doesn't go too far, which is what matters. And the y1 coordinate is 2 times x0 by y0. This one is easier to put in lookup tables later on the CPC, on the 8-bit, because it can be a one-dimensional table that stores the value, but this is a two-dimensional table. If you were to make lookup tables, we will see that later. And I add here the mouse y, offset y, the mouse y. So, and the final thing you calculate is this, I call it this distance, x1 by x1 plus y1 by y1. It almost looks like a radius without the square root, which you don't need it. And I compared, if it's over a certain value, it will break the loop, else it will continue the loop for 16 iteration, and it will, those x1 and y1, it will store it in x0, y0, and it will feed it back in the algorithm here recursively. And at the end, the color is based on the, I save here the escape iterators every time. So if it breaks, it has the I value that it broke. And the more the escape iterators compared to the total iteration, this goes to 1, it starts from 0. So outside here it's might be 1 iteration, here it's 16 iteration. Also, if you put more, you might get more elaborate shapes. Maybe too elaborate, a bit noisy. It's funny that in the shaders this is pretty fast. Pretty cool to play for, and the shader sandbox is really cool to try a lot of stuff. You can say, okay, what if I make this into 3? You make some different shapes. I could have more weird fractals. Can do some pretty wild stuff, like spiral galaxies. But anyway, this shows how much you could do if you play around, and I only did the regular Julia. The way I started this back then was I started with two values, and then they normally go from minus floating point range to plus floating point range. For some reason it's 0.016 floating point, but I multiply everything with FP more. This is to make it into a fixed point. How much is this one? Okay, it goes 8 bits, 256, and FPSH are. I would have written some stuff better now. And I think this is the escape value. Usually it's 4 times the FP mul. Even in the shader version it was 4.0. And I set up this initial as integer fixed point, but with a range di minus some floating point and multiplied it to make it into a fixed point. And anyway, I do it half the screen width and half the screen height for some reason. And there's a loop per pixel. Now, of course, the most obvious thing is that I'm going vertically from half height to 0, because I don't have the center. Do I have it? Ah, that's not it. Because you see, it is symmetric. From this line and below it's symmetric. So you could render, that's what I do in everything. Half the pixel and mirror in the bottom. That's a very obvious optimization that I did even back then. And I have unrolled my loop and I use a goto. Now this is a case that if you had a do while loop and break, and I've tried that, I've tried both versions, it would be a bit slower because you are doing the iterations, while here with a goto, hidden forbid a goto, you can escape, you can jump and escape the iteration, and this n0 is, it starts from 0. This is the index of the iteration, so that I know later and I put it into the color. And here I render the higher side and here the lower, the two symmetric half screens. Okay. And I'm basically doing the same thing I was doing in the shader. x0 multiplied by x0, y0, y0. But here you see, since these are fixed point integers, and they are in the range of 8-bit fixed point fractional part and 24 integer part. So FP mul is 256, FPSH is 8. This should have been defines and not integers. Are they even consts? Sorry for taking so much time. Ah, they are defines. Okay, they are defines. Yeah. Alright, I thought. Nowadays I have my defines with capital letters. And sometimes I notice micro optimization, like, oh, this could have been that. Because although I tried that and there was minimal improvement on the ARM, because shifts are almost for free. Yeah, but this is in a fixed point range. It's multiplied, so you have to shift it back. But if you add it to that, it's in the same range. It's in a multiplier range that has to be shifted back. So you can do the whole calculation here and shift it at the end. But anyway, I do that. I do the y1. You know, and I shift right by 1. This is really that. This is 2 times. I don't think I had to do the shift. I was a maniac with every power of 2 using shifts then, but I think the compilers At least this one would do that, even if I don't trust the compilers. And I shift the result back because it's another multiply by 2 fixed point, so you have to shift back. YP, XP and YP are the like the mouse position you have seen to morph around the Julia. And this is the dist, really. This is the dist. I call it MJ2. I don't know why. X1 by X1, shift. Again, this shift could be outside, you know, for the total result. And then I put the X1 and Y1 to X0 and Y0. It's the same thing to continue in the next iteration and in the next iteration. And I say if MJ2 greater than a value that I have defined up there, which is 4 times the FP mul, is the 4-0 I was comparing. Then go to end, then escape. And after the n0 equals 15, that could be 16. So there, you see your old codes, and there are a lot of things you can fix. Anyway, and for example, even that one, since this is for the next iteration, it could have been here, so that it doesn't unnecessarily load those variables when it's going to escape. Only if it doesn't manage to escape and it continues, it could go. I think there are micro optimizations. And in fact, let me see. Here is a version I did for the Game Boy Advanced. It's not as fast as I would expect. I'm looking into why. Because it's pure C code. I haven't seen the ARM assembly produced, even though I would expect it would be pretty good. And is that the source? Yeah, that's for GBA. Here I sanitize, of course. I have a fractional iteration block times 2 times 4 so that I can put it here. So if I want to edit here something, I will edit it here and not have to edit all the iterated blocks 16 times when I want to change something in experiment. And here I do it twice, of course, because at the end this is one pixel is 1 byte. I'm in 8-bit mode, 256 colors with color palette, so I combine the 2 pixels in one to write 16-bit values, because I think the Game Boy Advance is not just for speed. It will not work if you write 8 bits into the video RAM. That's why I have this 2 times, and because it's a go to, I have end 1 and end 2. Go to end 1, go to end 2. I have 2 versions in a way, but I can just edit this one. See here, I have the shift outside, the total calculation, and I do the shift -1, because this is like saying 2 multiplied by 2 FPS HR. It's the same. So I did some micro optimization like that. I don't know if they count or the compiler is clever. I put this before. I could have put them after the go to. But anyway, in order to show you the progress of how I managed to make this faster on the 8 bits, we have to go to the initial test. This was my framework that I use through SDCC with some inline assembly at the end. And can I show all of them? Yeah, that's an early repo. Okay, here it is. So that's back in September 28th. And that is 7 and then I move this to the pure assembly project. As I say, CPC 16-bit fractals work extremely slowly, of course. This is the first one where I managed to do it. And actually, that's a cool one. So this is a framework where I build as a debug. I will emulate the C code with how it would look on the CPC. And that's actually that early one is actually really cool. Oh, you see, I have moved the code from the Game Boy Advance with all the shifts. Important to notice that I reduced a bit the shift point. It's like 5 bits for fractional part and the rest for integer. And I use this type def for 16-bit integers or for 8-bit integers to separate, to reduce number as much as I can. And some of the iterations are with 16-bit integers, x0, y0, x1, y1, the distance. And then the color is in 8-bit. And I do the iteration twice because I have a left pixel table, right pixel table. I'm doing in mode 0 that are 1 byte is 2 pixels. So I have some pre-calculated table somewhere at some other place for left and right pixel. And this is okay. This is how it looks on the PC, of course. This is look. It was even pixel resolution. It's better than the one in the demo, but smaller though. But it's better because it's pixel per pixel in mode 0. I'm surprised it works so early. Looks cool. But mind you, this is the simulated video RAM of CPC with max PC power. So this is not how it will run on the real CPC. And let's see how it runs on a real CPC. So when I was in debug mode, I would run the simulated CPC screen. But on the release mode, it will do the real deal. Combines with SDCC. And does a bit of other things. At the end, uses manage DSK to build the DSK maze, and let's run that one. Let's see the options. 100% timing, no turbo mode. This is how it would, at the time it would run on the real CPC. Yeah, it works, but you see it draws slowly. It's not bad. It's not bad for a tiny fractal. And even pixel resolution, because in the demo I made it a byte resolution with 2 pixels and scan lines to quadruplicate the size, duplicate horizontally and vertically. So now if you put turbo mode, which means it doesn't say that, every opcode takes I think 4 cycles, 1 op cycle. This is to speed it up a bit when I'm debugging and testing. But yeah, the real speed is like that. So that's a start. Okay. Let's see at some later step what I have done so far. Oh, by the way, I have reduced the screen width and screen height to 32. This used to be CPC screen width divided by 4. So the original fractal you have seen was bigger. So if this is 160, it would be 40. But I think it was 128 bytes. So it could be 32 or 40, and this could be 50. But anyway. So one thing that I have reduced a bit the resolution, and you see some of it is out of bounds now. And I thought the 32 by 32 would be good for a start to reduce some values at the edges that after the multiplication they might go a bit too high, maybe just to start using my lookup tables. And here you see that's the old block, fractal block 1. I don't use it, and I use this one here, you see, fractal block 2 new. I have this, of course, in the iteration times, and then I have the escape block 1, escape block 2. Yeah, I had to do this because of go to end 1 and 2, because I do things for two different labels, 2 pixels to connect left and right pixel, obviously. And in the future code I don't need this duplication because it's 1 byte, 1 big blocky pixel that are 2 mode 0 pixels. Anyway, so the easiest thing to precalculate is the power of 2. So I cannot precalculate this yet. It will need an enormous table, but I can precalculate those. Also because if those x and y don't exceed, after the calculation they don't exceed too far, you could kinda make some x and y table later. So if you restrict your numbers in the very low regions, and you use shift 0.5 for now. So this is the new iteration, and you see I use the pow tab. Now xy could be from minus 32 to 32, for example. So you have to add the pow tab left, because the array will start from 0 to something, 64 values, 63. 0 to 63, so 64 values. It could be something like that is happening. So initially I had to do this offset because this value could come negative, so that I move it to the range of the table. Also in the future I'm doing some really cool tricks with that. For now I have that. Now this power tab left, I somehow make it's based on the screen width half 4 by this step 8 times the half of the screen width. Okay, maybe it's something from minus 128 to 128. But the important thing is that I make a power table for now, a lookup table. It's a one dimensional table, so it fits nicely. And so there is the value. And at the moment this is a 16-bit value, as I see. Oh, I'm doing this. I don't use this range in the moment. I think I'm using only the power tab here. I will talk to you about the range anyway. Let's see how this runs on the CPC. Compile. Maybe I shouldn't do this in every iteration. So the most obvious thing is to replace at least some of the multiplication with a lookup table, and that's it. Is it a bit faster? Maybe. It is a bit faster. It's still not real time. Also, it's also smaller. Pretty cool, huh? I could briefly show some steps without running everything. I say here fighting to optimize this a bit more. Some of the values inside the minus 128 to 127 range sometimes are made indent, so I made the tabs to be bite-sized so that the compiler will optimize it more, but much later it will be much easier for me in Z80 assembly to work with 8-bit arrays and 8-bit values as much as possible. So I'm just rearranging some stuff. Also, those are byte aligned addresses. Those are going also on the real CPC, so that some things fits in 256 aligned blocks for later optimizations. And I might not explain everything. I will show you later a memory map of where I put the tables at the end. This is going to be a big table, starting from 8,000 and taking 16K of space, although sparsely, it will leave some gaps in between. So here, for example, those power tables, I made them into 8-bit tables. I'm passing XP and YP are the, when you were moving the mouse on the shader to move around the morpher Julia, these are now 8-bit. And I fought a lot. These are still 16-bit. I fought a lot because I would do something on SDCC. Oh no, I would compile here on C, actually with GCC for the SDL project, the simulation of how it looks on the CPC, and it would be okay. And when I try, even if I use type devs for the type, when I went back to the SDCC, things would overflow when on this side they would not overflow. So there was a lot of fighting. Sometimes even literal values you have to cast them to 8-bit. There are a lot of traps with. Yeah, I'm using some precalced signs. This is a sign table 0 to 255 to move around the morphing animation, the XP and YP. And I'm doing two tables. I'm doing this table, which is the pure power. And this is a power. Oh, I'm gonna show you that soon. So I'm gonna try to explain this as briefly as I can. This is a newer iteration. I have this table pow tab, and I have some tables where I say SHR for shift right. Okay. And this multab SHR. This multab SHR, it's finally doing what you used to do here, x0 by y0. This is the big table, and then shift right. Okay, and previously I used to have this one. This is the one I had. And here you see there's only pow tab. So it's a power of 2 table. And I shift right the result. The thing is, if you have this, and if this is 8-bit, result will be 16-bit range. Not range interrupt. Okay, and that's the thing, that if you multiply that with itself, it's a fixed point that will go to the 16-bit range. But what if we could fit everything in the 8-bit range to simplify? That's what I'm trying. That's why now I have 8-bit tables. But those tables are doing shift right, because why store? Here I'm storing this value. This is HL, not H1. Looks like 1. But if some of my calculations are multiplying and then shifting the result back to keep it on the fixed point range, which is 8-bit range, why not do the precalculation with the shift so that the final table can be in 8-bit, can still be in the 8-bit range? And this is how I made some of the tables staying in the 8-bit range, which is great. So that was the old one that I was doing separately the multiplication, and so it went to the 16-bit range and then back. And this is the new one, or at least this is an 8-bit table, and this. And the only issue is here, because in the I don't have the old code, the original code. Just wait. So this is the part where I switch from pixel mode to double pixel mode, so that I make it a bit bigger, and it's still smaller than the final. The movement is weird, of course, because I changed things. Double pixel and scan lines. And I was in the middle of trying to do some more things. Oh, by the way, you might see again that this is the original. I brought back the original macro for testing. So when I tried to use tables, things sometimes didn't work well. So I had to move this iter block, and here is the one I use, and I could switch to all of them. So I could switch to that, run, maybe three works here, but it might not work on the real CPC when I switch to compile for the SDCC because of number ranges and other stuff. So I think the difference is here. It's the same tables. I was testing this because this might not work on real CPC yet. Actually, let's try it. Oh, and as I say, I'm using. See here is the iteration now, and I'm calling render Julia pixel. I have separated the function so that I can more easily work with it. 10 iterations, and I'm using a single table that it maps the iteration value to one big pixel with 2 mode 0 pixel, 1 byte. So I don't need to do the previous step where I have left and right pixel twice. So even those defines are fewer. So if I am to build it for CPC, let's see, am I building iter block 2? I don't know what will happen, because some of these commits are in the middle of things and they might not work. Now there is a small time where it pre-calculates the tables. It's not so big, maybe a few seconds. See, this is wrong now. Something goes wrong with the numbers in this step. So these are things that I would gradually fight. Not even block 2, let alone block 3. I don't think block 3 works. Block 1 might work. But that's the old one, where I was doing the multiplications. So that was a very gradual process, all I want to say. And I'm moving commit by commit so that I can talk about some things. Now that does work in this low res resolution, but of course slower. And there is a lot of process. So here is the point escape tab works, where I implemented my last early idea on the pure C code. That is, I minimized another table from 16-bit to 8 bits. I'll show you. And maybe we'll show the real code. And this one also, the previous one would, some of the precalc tables would fail on the real CPC, but this one will work here. I will build on the CPC. and do the numbers explode? Long pre-calc. Oh, it works. Still slow drawing, of course. It's a bit of a step ahead from this one that even half of the tables didn't work to this one where I implement the last table and it even works. So that was 29th of September and 30th of September. I might have skipped a lot of things I didn't commit it here. It doesn't matter. It was constant finding with the numbers and making the tables work. The tables usually, and even the math and the different ranges of number work better here. Even if I force things to be 16-bit and 8-bit integers with some type depths. And then when you try to build it, it doesn't work on the SDCC, on the CPC side. But also now this one works. So now I have to explain a few things. I have different blocks, but I'm using only this one. I keep this one for references. So if something fails here, I'll go back to the previous one. Oh, I see this one is still doing the multiplication. So maybe I'm not complete. Maybe this one is using all the tables. This one will work. Oh, you see, there is even overflows. There are some overflows on the edges. So I was still fighting with that. But I make the escape tab work. And that's the important one. Because that step is this step. This is where you calculate the double power. You don't shift those values back normally, although you could. Because you have to compare it with the escape value. And I simulated with using the power of 2 table twice. Okay. But the result, MJ2, is a 16-bit, and we are trying to make everything fit in 8-bit. These are back to 16-bit for some reason, because I was going back and forth. So, and here is, if you try to pre-calculate that alone, here is the trick. You'll end up with a 16-bit value. Unless you store a shifted right value, I guess. But maybe the escape won't be very accurate, I don't know. I haven't tried that actually. So I had an even better idea. Although, you need to make another big table. And here's the thing. An escape table. Which is... It will be an fxy esctab gives you either 0 or 1. False true. You know. 8-bit array. It's an 8-bit array that you plug in x and y. Now usually x and y, because the numbers are small, x or y is in the range minus 32 to 32 maybe. And that's how I can fit them. So this is, I'm just using some similar. This is 64 by 64 because it's going to be in x squared. This one is going to be in x squared. And this is, it's 4096 bytes. But because we want to be byte aligned, this is at address 8000 and goes till address, is it BFFF, I think, before C0. Because we want to keep things 256 byte aligned. I will show you a memory map later. Although, no, by now, I think I shift right by 7. I multiply by 128 for some reason to get the scale. Now I don't have it. I have it starting at that 8000 address, hex address 8000, and maybe I'm storing minus 64 to 64 or something. I don't remember. I'm just doing silly stuff here. And you see it here. The magic is that if you store an escape tab that is based, see, I'm doing the same calculation here. The result is 16-bit, but you need to store only if it's smaller than escape, you put a false, 0, else you put a true. So I end up having a table for an n squared x by y array, but it's at least it's 8 bits, so it's easier to feed, it's easier to read. So, and I never, in my final solution, I never do this. I never use the pow tab twice here in the 16-bit. I never do the comparison. In the final solution, with y1 and x1 with some offsets, I do some shift rights for some reason. I don't remember why. Maybe to fit some numbers would explode. But the gist of the idea is that within x and y, I can tell you directly if you escaped or not, without even calculating this. I can tell you directly. So it's totally pre-calculated with a big x and y table, and then you have this x by y, which this block 3 does it, but maybe it doesn't work well at that stage. It works here. Oh, even here it has overflows, as you see. So there is a lot of process with that. We have to move on though, but that's an important idea. How I started minimizing things. So I don't even have the new version. The real version would use this multi-base HR. Here you see again, yeah, this is 6 and y2. So it used the y0 shifted right by 7. Maybe I did it 128 in the width. Plus x0. This is a two-dimensional table also. But here in this solution I don't use it because I still had issues. I was going back and forth. Ah god, I need to move with this. I'm sorry that it takes so long, but I might have to show you a lot of the steps, or at least the most important ones. I had some back and forth for an hour because something, as I was moving, something wasn't working at all with the new SDCC conventions. Also, I have switched the compilers back and forth, the old version with the new. Because at this point I went to the more recent compiler and I had some new flags for the convention, which I was using. I don't know what happened. Because when I switched, I used those conventions too, and anyway. So here, for example, I still cannot figure out whether the CPC version falls with some tables. I'm just showing you highlights. So here it works on the PC when I compile for the SDCC. Okay, now it's going faster. Remove turbo mode. Go to normal speed. And here are some examples of some overflows with the pawn tables and some other stuff. when it goes out. Pretty weird, eh? So this version doesn't work, but I can go manage to rewrite it in assembly. Can't believe that it works. Although that one, I go somewhere there and skip here, skip all of this. Something went bad. So now we went step by step. Let's see. I'm going to start explaining some. This is the slow assembly. This is the original version. Let's see if it does work, because previously it wasn't even the number. It was crashing because of the change in the calling convention of the SDCC. Even if I took care of them while I was moving from commit to commit. It's normal speed. Yeah, it does work. Okay, that's the first assembly version. It almost starts being like 1 frame or 2 frames per second. Whoa, it's going there. And all I did was in pure experimental mode, in pure C, I tried to make everything work with tables. Everything, no multiplies and so on. So I had some much slower C version. And now we have something that runs slowly, but it's almost there for real time. And I rewrote the iteration. Here are the iteration block. This is much bigger than the final one. I rewrote it in assembly. Oh, and I did some more stuff. Oh my god, I have to explain all that stuff now. I was hoping for the video to be smaller, but it's impossible if I want to go through a lot of steps. First, the minimization in C. The minimization of the algorithm to the absolute simplest thing, and then the assembly. And then we might go back, because there are some tricks in how I store the tables later. So this is the final one I used. This is the one that runs in C code. And I say if dev project CPC, then do it in assembly. Else, do the frac iter 8 times for now. For now I did 8 iterations. Frac iter 8 times. It goes back to the block new. So this is what's iterated. So this is the one I try to mimic in assembly. So I might put it near here. So we can see it, maybe. Maybe, I don't know, maybe here. It might also help to, I don't know, put it here. So we can see it color. No, it doesn't matter. So we do the same. We have the POTAB SHR. It's an 8-bit table, multab SHR. So it does the x0 by x0, the power of 2, and then shifts right in the result of the table. And this one, I see now my shift left here, it's 6. It's multiplied by 64. So the width of the table is 64, because the value are minus 32 to 32. So I have them stacked into They might be aligned, but not entirely yet. So to go to the next if mul tab shr, if it goes this, it's psi by 64 plus he, or psi shift 6 plus he. So I have to do this shift 6 times, and that's not good on the Z80 assembly. And I even have to do it because the final value will be a 16-bit address. I had to do 6 times add HL, HL. After I fill HL age with 0. Now that's important for later. L with the value of register C, which C might be the X0. And I do it here, L with the value of A. Now this is, I'm not going to explain everything, but I'm trying to minimize to use register as much as possible. And it happens that, okay, this value, I get that from us. This is the starting value. In SDCC, when you call the function ix plus 4 will point to the first argument, ix plus 5, and the second argument, if it is 8-bit, if it's 16-bit, you are going to get the low and the high byte. So at the beginning I get on B and C, x0 and y0 will be B and C. Much later in the iteration, I will feed those again from the previous values. This one, for example, is at this point D and E happens to be, and then you do this x0, x1, y0 is y1, and that's why you do this basically. And previously in the above calculation here I see E and this x1, y1. I might not go into much detail because it's too much. I'm gonna tell you some of the stuff I did. I know I should have prepared that. So this is something we minimize in the future because that takes too long. It takes 3 NOP cycles every add HL, HL. So you might see some shifts here, and you think, okay, if this is on x86 and especially on ARM assembly, this is almost for free. Okay, I can have a 2-dimensional table with power of 2 width, and that's fine. But this is not ideal for the Z80. Also see, I do everywhere LDA, 32. Okay, that takes 2 NOP cycles, and add A, B. I have it a lot. Add A, 32, add A, 30. What is that? Is this offset shift? Okay, in those tables. This happens to be 32, I think. Because as I said, all these tables you have values from to 32 range. So PO tab SHR 0 is really minus 32. PO tab SHR 32 is going to be 0 and so on. So you have this minus 30 to 32 fed into the lookup table, and it calculates the POW. You know, like minus 32 by minus 32, minus 31 by... I could have used symmetry, but I didn't need it. So, as I say, you have to offset, and this is an additional thing. This is much... It doesn't just 2 NOP cycles every time, but we did some tricks for that one too. So this is to move the initial x0 that happens to be B, register B at this point, and y0 that happens C, to offset them. What have I done? And we do similar offsets there too. And we put them back to offset them so that we can later use them with the table. I put H F4. I think F4 is Pow tab SHR F4. I much later use the define inside the assembly. I much later do something like Pow tab SHR. Was it the address? I do that much later to make it easier to read. So this is the high byte. Things are byte aligned, and the low byte is the value. So the table starts from there and goes positive. It is the same for the other ones. I'm gonna have a hard time to explain everything. Now we were on this step. And here, see, commit the backup some more insane optimizer in the middle of this. I don't know if this will work because I was committing stuff to save. Where I don't need to add HL, AHL 6 times. The minus 32 is mapped on overflowed low byte in the Y I stored the arrays. Still one more to store in that particular way. So yeah, forget that. I was testing things in back and C. I was going back and forth to see if this. I was storing in C and see if it works, and then going to assembly. And here you see all this thing, add HL, and all that stuff. They are minimized. I do a push and a pop for some reason. I don't do it at the end. Trying to avoid it's expensive. And just for my test now. So I've minimized that a lot, all those shifts, and I'll show you how. I need to see. Mul WSHL left, WSHL, yeah. So I'm storing my arrays differently. I'm still at 0. I don't know if I do all the tricks, I'll see. Let's try. Hopefully. Okay. Let's see if it works now, because I don't know. Let's see that optimization. How much if it improves, if it works, if it improves, because I don't know. And I need to explain that, because there is more. Oh, it works. It doesn't seem faster. There is a silly reason why it might not. Oh, or maybe that's later. There was a point in my code where here I render half of the Julia, and with symmetry I complete the rest. At some point I changed something and I was rendering fully the Julia, and with symmetry I would render it twice in a way. So I don't know if this improved much. Still seems it has a lot to go. I think I have to explain some more on the Z80 side, some more weird stuff. You see here, auto M, this is a code auto modification that I do once per frame. XP0, YP0, and I say add a, 0, but this is not going to be 0, add a, 0, XP1, this is for every iteration. And this is okay because it's called once. This is every frame, and then the render Julia goes every piece. This is called once in a frame, so it's not. It's all right to auto modify code. So I'm getting the XP and YP. So these are the values for the Julia morphing. These are the values from the mouse, from my shader, for example. These are the values that move around to make the thing move. So I had this idea to auto-modify this code. And one reason was that at this point I didn't have any free registers. Okay, I would either have to read the value to add. So A might have this value before you add the XP, and later this value before they add the YP. And because I try to minimize the use of register as much so that I don't have to use I use the IX only in the beginning to get the arguments, but not later through the iterations. I was out of registers again. I don't even use the EXX inside here. Actually, I use them from the outside later when I call this function. But during the iterations, I'm using the few 8-bit registers. Because I wanted to minimize, I did this auto modification to add the XP and YP. So every time when the XP and YP is moving, they are auto-modifying these values inside for all the iteration. But that happens once per frame. So it's pretty fast compared to. And I save the reuse of register or having to push and pop registers. That's another micro optimization I did. And it gets better. The way here, yes, I remove the add AGL 6 times for this part, but there is another part. Because you have the table. Let's see. So one of them still remain. You have the POW tab SHR. No, the MUR tab SHR. It's based on Y and X. 2D table, and the escape table is a Y1X1 table. So that also is feeding with that edge. So I did the same for that table. Whoa, optimize most, still things to do. I reduced the add HL for the escape table too. And here you see I need to see what I did. I used to shift by, that's the mul table. The escape table is here. I calculate the index of the table. And now that is shifted 256 times. I must show you that. Now it's time to show you. But let's... I know this is going to be big, but... what can you do? And now I have to show the grand idea. And how it evolves. Curious how this run. No add HL, HL 6 times. For both. Oh, see. Now it starts getting somewhere. I could have released it like this and be like, oh, real-time Julia. But it's faster than this. Now it starts being an effect. At this point I might have to show you some of the memory mapping of the tables. And maybe I'll start with this one. So let's see. Oh, it loops. Okay, let's go back. Now it might not. So, for example, when I have the one-dimensional power of 2 tables with array ranging from the indices of the array would go from 0 to 64, but the numbers stored would be from minus 32 to plus 32. Now I could have done 0 to 32 and check for negative sign and mirror it to save space, but that would take time in the iteration. So my idea is to have pass the minus 32 to 32 8-bit signed to the array and retrieve the real value, the power of 2 value, even if they are double values, instead of checking for negative sign and reversing it. And the original storage was like that. This is a 256 bytes align table. So the high byte in the address will be the same, and the low byte goes from 0 to 255 FF hexadecimal. So that would be the regular way to store it. But then, if you pass a coordinate value that can be negative or positive, you have to offset it. You have to add plus 32 to find the index on the table. So I thought, why not do a trick and store the values again in a 256 byte aligned area, but the negative values will come from the other side. So here is 224 hexadecimal C0, but as a signed in signed 8-bit it would be minus 32. It goes to 255 FF minus 1, and then it wraps around from the positive from 0 to 32. Actually, it's 31 till 3F. But I could go further. I have left some gaps. I could have bigger numbers, but I didn't left because vertically I have some issues with the later tables. So now the high byte, I prepared the high byte before to point in the same address on the 256 byte aligned table, and after I do my iterations and I get a coordinate x0, y0, x1, y1, I just pass it as it is. I don't do the offset. And it happens to map in this weird overflown table with gaps in between. But this has to fit in one 256 byte area aligned in memory where the high byte is the same. And then I updated this concept in the 2D arrays for the multiply x by y, for example. And the original, the old one, the one that I had to do 6 add HL, HL to shift left by 6, it had stored, okay, these are the values minus 32 to 31 for y0. These are for y1, so I had them stored packed together serially. But I had to do this shift left by 6. And actually, at some moment I thought it would be faster to have another lookup table that gives you the multiply by 64 or shift by 6. I could have used another table, but the thing I did was much faster at the end. And you can see it here actually. So that goes like this. So I could have filled 256 bytes. I could have from minus 128 to 127. I could have a whole line and I could increase the high byte to go to the next Y. But then I wouldn't have much storage for a lot of vertical values, you know. It's hard to explain. But anyway, I did the same trick. I did this with the one dimension table. I did it here. So this line is 256 bytes aligned, the next line is 256 byte aligned, but the high byte is increased by 1, 2, 3, 4, and this maps vertical to the Y and horizontally to the minus 32 from the right side, overflow to 0 to 31 on the left side. So if you pass me a low byte, that is the horizontal x-axis, and it's assigned value minus 32 to 31, this maps directly, and then you pass me the vertical value and I load it in the high byte on the register very, very easily, and I immediately have an x plus y very, very much faster map. The negative, of course, it takes more space. it takes more space, and there are gaps. Now I could use those gaps for other pre-calculations. And the funny thing is, if you were to look, not the one I have in the current commit I was showing, but the final, because I did more tricks. Maybe I'll show you that now. If you look at the total memory map, you get this, which is a bit insane. It's easier to say. This is the escape table. Okay, every one of these squares, the four big squares, are 16K of RAM. The video RAM is placed here. Okay, here is my escape tab, escape table, x, y, minus 32 to 31 for x and y. These are the ranges. So it's 64. 64 vertically. Because horizontally I have the gaps, I can only have 64 vertically. You know, else it will overflow in some places where I have code and data. So I fit that exactly there. And the low byte will map directly to the x coordinate, the signed x coordinate, minus 32 to minus 1, 0 to 31, you see here. Okay, I will place the high byte when I'm going to feed this table. I will place it here, not at 8000, but was it at 0x A00? I think that was it. I don't remember. We will see. So I will place it here. So I will add to the offset of this the vertical coordinate to go minus and plus. And then the low byte will just be fed directly to the total 16-bit address. So I will much more easily map this with much fewer Z80 assembly. And this is the crazy, the multiplication tab. We need to see something. Right now the multiplication tab is sitting at 0 in this example, which I haven't done all the tricks. You know. And I think I need to check it. I think I'm still adding 32 to the address to get, if it's that's the one. I don't remember. At the beginning, this area was the red. It was going to 0, it was going here, and my code was here. But then I moved it. That's the bigger trick. We will see later. So that now it overflows over the end of the 64K and it goes up from 0. So you can pass the y coordinate as the high byte. If it's negative, it will map here on the top. And if it's positive, it will map in the beginning. So I have a big array that is not exactly 16K, it's like 4K with gaps. And I mapped it in such a way that this is the whole 64K memory. That it takes the four corners there so that the x and y for that table, for the multiply table, map directly to what needs to be read. You know, I couldn't do that for the escape tab 2 because there is only one place in CPC memory where things overflow over 64K and go from 0. So it's kind of crazy to explain. And in this, the current commit here, I haven't done this trick yet. It comes later. So there are a lot of micro optimization. There are some that are not very significant. Maybe I could skip them, but here I say, oh yeah, that was fun. Maybe I will explain it very shortly. So I used to do that. I use the power table for the x, for the y, which represents this, and then this, and then you add the xp to move, you know, to morph the Julia. with the offset on the X. So that's not it. I just added that now to show you something. I think I separated that. I thought you can write this like that. In that part, I have added it to a new table, because that could be one thing. However, XP changes. So what I'm doing here, I have a POW tab SHR add original in an address. I point this one in another address, the next to 56 bytes. It's a stupid micro optimization, although it was important. And I don't have the values for this table because this changed based on the movement on the Julia, but this value changes one per frame. So every frame I loop, I read the values from this table. It's an 1D table, so it's only 64 values from minus 32 to 32. Just 64 bytes per frame. It's not the heavy duty per pixel iteration, Julia. And I add the offset and copy it below. So I have the original table and the table with the offset that I recreate every frame, so that in the iterations, you see here, I do this add. Okay, that's 2 knobs after the results of the table. This is the XP I'm adding, and I'm even doing the auto modification, but that's not. So that goes to gain another 2 knobs. So there are things like that. And now this has gone away, all this auto has gone away. And maybe I saved some register or something. Yeah, because I had to read. Yeah, there is no point to explain that because I have to somehow describe what I do. I don't do the auto modification for the XP. I do it for the YP because I couldn't do the same trick for the YP because the YP is added outside on this whole thing, and this is a 2D table. It's the multi-tab, so I can read the whole 4096 values and add to another area in memory, another 4096 with the YP offset. It could be more ways than just adding it there. So that was another micro optimization I did. Maybe we can go gradually. Okay, it didn't complain. And we can build it. It's a micro optimization, so you won't see any difference. Okay, let it run, and let's go to the next one. More optimization. I might have to skip some of that stuff and go to the important stuff. So after the bigger ideas, I did the more optimization of the. Okay, this is not important because like I have the assembly part, and I still. That's the funny thing. I'm still doing the pixel loop in C. Because I wanted to optimize, no, but not on the final intro. It's all assembly. I thought, okay, it's the iteration that will take the most time. So for the prototyping, the per pixel loop is in C still, but I just optimized some stuff. I think I would get the vertical Vram lines by doing some calculation, get it from the array. I just get them much faster. Those are just some micro optimization. Later I will write this in assembly. Let's move one by one. And I tried to rewrite the main loop in Z80 assembly, very crudely at first. Unroll the loop inside the main XY loop. I just inline the calculate Julia per pixel iteration inside the XY loop. Maybe I wouldn't show. How does it? If dev project CPC, I still see it here. Oh no, this is removed and this was inlined here. It's no point at the moment. I might come to this later. So now all the pixel loop is happening in assembly. I have an if dev project CPC, else if I'm running the debug SDL version, it runs the old algorithm so that I can debug, and I say final version. And that's the final version. Let's run this one. I increased the dimensions. Ah no, that's the position. This is where I'm doing it 24, minus 24 to 24. Compare with 24 for the loop, so it's 42, 48. 48 bytes width. In the height it is minus 16. Vertically it's minus 16 to 16. It's 32. So the effect is 48 to... Let's see it actually. Let's see at this point how fast it goes. So it's a bit better vertically, but horizontally it's 32. That's why later I make it a 48 by 48. See, the more it moves, it gets bigger and it gets faster. So let's see how it runs at this point of time. And we haven't done everything. There is more. Some of it I explained, and there is more. Oh, do you know why it's slow right now? I was seeing it and saying, oh, it's maybe because it's bigger. Let me see. At this point, in this comment, I was like, yeah, I did all the optimization here. It seems, okay, I made it a bit bigger, but I was expecting it a bit faster. Is it slower or is it me? So this is the vertical. Remember that I was doing symmetry. So I had to go from minus 24. This is the vertical coordinate of the pixel. And draw half of it, and the other half is mirrored. Okay, and I have seen minus 24. Increase C. I put it on A, and I compare with 24. Idiot. Idiot. Inc C and then not 0, it will go to 0 there. It might. So it goes faster. And so there was a point where I was optimizing and I was like, it's good, it works, but maybe it wasn't as faster as I thought. I had the faster version. I did this mistake because it's mirrored. See? It's mirrorable. I was drawing it twice at this point. Thankfully I found the bug later. So this way it's already running, but it's not I have gone further. That's the point where I started quarter Julia subdivision. Okay. Look, and also in this project, okay, I have rewritten in assembly, but I keep the C version because I'm going back and forth. I'm trying something on the C side, so I have a new idea. If I can render Julia, see, here I'm skipping 2 pixels. So I'm calculating, I'll show you. Very simple, the idea of subdivision, it's very common in in graphics. It's common in ray tracing. You know, like the Heaven 7 intro and others who have used it. And sometimes it works with fractals. You can get artifacts. You can have false positives. I mean, everywhere. So, but with such a small size and the 2x2 subdivision, the idea is I calculate, this is the first pixel of the zoo. I calculate this pixel. Oh, look at the, okay, it doesn't matter. Then I calculate this pixel, this and this. So I skip every 2 pixels. And say that here I got this color, and maybe here I got this color. So I compare, even if it's this pixel and this, I'm going to decide what to do with this 4 pixel, even if I go 1 pixel later. Because if I calculate this 4, I would have already, I want to skip this pixel. Yeah. But these all come, if they come the same color, same iteration on the fractal, I'm done, and I will paint those 4 pixels the same. Okay. And I'm done with that. Then I move here. Okay, 1, 2, 3. Oh, that's a different pixel. This means I have to calculate. This may be outside than the 4 ones I want to calculate. This one I have already calculated. And that's how it works. I see the nearby and I say, okay, they are not similar colors. So maybe I have to calculate this. And oh, this came a bit different. So it was a good estimation to paint those. So these 4 pixels, I had to calculate 1 pixel for 4. I did 1/4 of the Julia calculation. But this one I ended up calculated all 4 pixels. So this is a way in certain regions of the Julia to calculate 1/4 of the pixel and decide to paint the rest of the pixel the same. But if you go to the more detailed Julia pixels, you end up calculating all 4 from the 2x2. That's actually what subdivision, that's how roughly it works. And I thought, hey, why can I not go further with that and do some kind of subdivision? And let's see, I did this on the PC side first. So, but only on the PC side. This is doing some, yeah, it's a bit jumpy, but because I move it slower. So I did something like that in pure C to test. Render Julia quarter is going to render skip 1 pixel. That's why I say this is the coordinate of the pixel and I go +2. And I temporarily store this in a Julia quarter. So I store the points so that I can revisit them later here. And it's simple. I read the 4 neighbor pixels and decide if this color is the same and it's the same with the other 2 colors. If the 4 colors are the same, just write this value, which is already calculated, in the 4 corners of the pixel. Oh, this is for the symmetry below. Okay. Else, you have to call render Julia pixel 3 more times. The one is already done here. So I don't recalculate all the 4 pixels. I calculate the rest, you see. This is the coordinate of the original pixel +1, vertically +1, and horizontally and vertically +1. It's that simple. And then I render those values. And there are two lines because this is the symmetric below and this is the above. And I tried this on the C side and I was like, whoa, that actually worked. That could optimize the Julia more. So pretty fast, revert the calculate single pixel code to be called instead of inlined. Yeah, because now we will call the calculate Julia. We have inlined the assembly version inside the main loop, but we are going to call it. So I'm like, I can't inline it 4 times. So I reverted some things for the new method. Oh my god, while preparing, I realized the bucket made to. It's that thing. I was trying the whole thing. Even if I copied it symmetrically, I was calculating the lower area, and I realized it now. You see, compare 24. I still do compare 24. Minus 24. Oh, have I changed that? Anyway, I'm gonna check that. It's going to be funny if I did that. Where is it? Switch. Yeah, so I'm doing some stuff. Ah, that's the interesting one. Here I'm testing. I haven't done the full subdivision, but I did a crude test with skipping every 2 pixel on the Z80 side. So I haven't done the subdivision where I compare the 4 pixel and I just render blockier pixel just to see that. See, this is the 1/4 of the pixel rendered, but for everyone, so it's blocky. And this will be expanded to the accurate part to go and calculate every pixel. So this is how it would look if you did 1/4 of one, yeah, skip every 2 pixels horizontally and vertically. Yeah, those are small changes. Oh, I say that this works now. Okay, I'll check it. That version, I finally did the whole thing in assembly. That was the original code. Okay, but here, call render Julia quarter. So here, I'm skipping ink C, ink B, but compare with the fx width half. Here ink C, and don't do the same mistake. Go twice in height. So I calculate every 2 pixel. Now this looks like a bit weird code. I'm still stuck with it. The thing is, because there are not enough registers, I have C, B, I use HL and others. One way, and I want to pass things on render Julia. Now render Julia is using the extended register. It's using a different set of registers. So I wanted to pass B and C, which are the coordinate X and Y. But because I'm using this in, here, even here, I'm using them in a loop. I have to do it, pass it to A, do EXX, pass it to B, go back. These are the extended. I love those registers. And now one way would be to do a push BC and pop BC later. But that would take 7 NOP cycles. This is taking 1, 2, 3, 4, 5, 7, 8, 9. Actually, it would take. Does it take more? Now, this EXX is necessary though. Because inside render Julia, I'm using totally the extended register, because it's not just BC, it's the HL I need here, it's especially here I'm using more registers, and I want to do this pass. Maybe it could be done better. And I found that the push BC pop BC is not better. Maybe it's worse for one op cycle. I had to do an EXX anyway. You had to do an EXX, no, push BC, EXX pop BC, and then EXX. So it's 4 knob cycles and 3, 7, 8, 9. This EXX you have to do it. So now it's 1, 2, 3, 4, 5, 6, 7, 8. It's 8. And I was putting my head to see maybe there's a better way. Or maybe I could avoid using the EXX and do some other thing. So the render Julia pixel is working with the auxiliary register, the EXX register, as I call it. But outside in those loops, they are working with their own registers. And here I calculate the Julia. And that's the address of that temporary table where I store the pixels calculated in the skipped version. Skip every 2 pixels, which here render Julia from where I finally read them. And I'm using IX and IY because I have not enough register, and I know those are much slower. And I was like, what the hell, since the heavier part is on the iterations. Maybe I could save some more, but I couldn't find it. Oh, and there are more stuff I have saved later, which I might have missed. So here, I found I use IY, IX and IY because I found, since I want to go put A to IY, the pixel, go to the other pixel, 2 pixels on the left, down and right. And I do the 3 comparisons directly. I don't need to see LDA, I don't need to do that, or LDB if it exists, and then compare with B. Because I do it directly, and if it's not the same, you will escape early. If we find one pixel that is not the same. So here, I'm going, it's very complicated, maybe I shouldn't explain. Here I call 3 times the render Julia to render for the 3 other pixels I didn't. So if that fails, if the 4 pixels are different, I end up here, else I'm writing, here I'm writing the same value, the value is here. It's taken here, so I'm writing here. I do some trick with set res. Maybe I shouldn't. These are tricks that are known on the CPC, because normally if you are in a line, if you are on C00 in the video RAM, although now I'm in 400 because I moved in another page, it doesn't matter. If you want to go one line below, you have to add plus 248, else you have to add plus 49. And usually you did it add HL, BC, LBC, you do it like that. So because I want to go to the pixel below, or the byte below actually, and actually the byte below after 2 lines, there is a trick with the set and res. If you see how the addresses changes as you move to the next line inside a character, you will see it's faster to do this than do add HL, BC, because this is taking 2 knob cycles, set bit and reset bit. So with all this thing, if I have 4 pixels, I move from here to here, then down, then there. Actually, I might do it here, 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 and then increase to the next pixel. So I can read the 4 pixels as fast as possible with the same A value that I calculated. But if one of these comparison with the original, with the nearby pixels fail, it will jump to the other thing. Oh. I think at this point I went too far with this, and I'm reading this. There is a lot of Greek fucking calling conventions. I don't know what. Add a tiny font FPS. Let's see here. Let's go here. Let's go a bit far. Oh no! I was doing stupid stuff here. Hopefully now. So I think I explained the majority. There are some tricks I want to explain. At this point, still at this, let's see. Let's see with the frame rate counter at this point. Oh, now I made it bigger, of course, you see, and more movement. Because I realized there are so many things, and I'm explaining the majority. There is one thing important with the table, which I have shown. And now, oh, this is the double pixel. I duplicate the scan lines also. It's more blocky. And some people will say, yeah, maybe that would be better. You should have used that one. This is going now, oh, it's still going 6 frames per second. I did more stuff to make it 10 frames per second. I did something crazy, which I explained in my schematics. Yeah, that's a nice version. It's double pixel. I prefer the scanline version because you couldn't see as much the... So this is not... The final in the demo goes 10 frames per second. And even that could be better. And you see I have the colors a bit jumpy because I changed the interrupt mode. I had the... Oh yeah. So this is the thing I haven't done yet, and I prepared it. Do you see there's multiple... this is not inside yet. This is what you have seen running. It's not like this. What you have seen running... Okay, I think I need to... Right now, forget about this. Right now, where is it? Right now, the multiply tab is here. It's not high. It's not relocated in the way I'm showing the red thing. And that was the big thing that saved a lot. So right now, among other things. So this memory map is of the final. This is what got me from 6 frames to 10 frames, I think. And we will see how. In order to do this, in order to relocate the multiply tab to overflow over 0, I had to change the interrupt modes. Because when the CPC starts, it's interrupt mode. Interrupt mode 1 means this is where your interrupts run. Interrupt mode 0 is vector interrupts. You can place it wherever you want. So, with interrupt mode 1, which is the default starting, this is a problem because the interrupts would be sitting somewhere here. Actually, now I'm thinking it. They are sitting at 38. 38 is... It's over here, is it? 38 means 48 plus 8, 56. I now realize that it wasn't entirely necessary because they would sit in this area. which I don't use, in the gap. But if I had a very big interrupt routine, it would bleed here. But I could have a jump here that jumps somewhere else. Okay, so that wasn't there. I never thought about that before. But this is the reason I say relocated the IM2 at... I already used the IM2. Prepare some defense to relocate IM2. So I started using the IM2. I was doing a new framework at that point. Let's see. Notice that I changed my framework so I can do all the steps here and not necessarily do it for the CPC. And I added more steps later. I was adding more binaries with managed DSK, and I have a new demo system at some other place for as I was preparing the demo for this. And that's where it is now. So this is with the scanline version. You see it goes from 6, 7, 8 frames. So it's getting a bit better, but that's not the end. We are approaching the end. It's just a lot of Z80 optimization. You start from the original. Without the wraparound trick on one of the... I might start doing this stuff, where I move the tables to wrap around the negative and the positive. And especially this one is important. You know, it's hard to describe anymore now. I might have saved something here. Although I don't see it. Ah, yeah, I have commented out this one. See, that was the offset, plus 32. There is the question mark there. It's a Greek question mark. So this is commented out. Gain 2 knob cycles. And then I say some crazy optimization, more to come on the Z80 tutorial. I momentarily replaced the red and Z with the GRZ and it fails that. I didn't see any gain. What did I do here? It's hard to see. See, this one takes 2 knob cycles, this one takes 1 knob cycle. I realized I could use some value from later. I think I know what I did here. I'm just saving off some things. Here is when I'm rendering with EXX, I'm preparing the table start addresses. And the ESC, that's what I say, the ESC of tab. The ESC tab address is 8000. At the end, I'm passing the 0xa00, which is in the middle. I pass it on the high byte, as you have seen. I prepare it before I even call for the Julia, and I try to not touch those registers. I pass it on E, but later I might copy it on H to create the HL pair. So this happens to look there, so when I get I might get this value and add it to this one, and then store it back to H. So I was doing some little things like that. Those are not the biggest one. Let's go gradually. We are about to finish, and I'm sorry it took so long. And I can't help it. And this is the wraparound table. From 0 back to actually the opposite. This is the trick where the mul-tab was at C00 to the end, and it starts now from here and it wraps around from above. Okay. This is the trick. I think that's the trick. And every time I do that, I have to go here where I'm pre-calculating all my table. This is still C, but because the pre-calculations. Much later, when I transfer it to 100% assembly for the intro, I would have to rewrite this in assembly too, because the C produce code is... It's very nice to prototype things and initialize some things in pure C. So the way I initialize it, I do end 65535. It's such a way so that it will wrap around from negative to positive on 0. It will start from here, will go on the end and will wrap around here for the positive y values. And that's the funniest thing, because when I did that, here are the iterations. I simplified it. Previously, you would have all these paths, and here you would... This is the plus 32. You put tab left y, which is 32, on A. You add the C, which is the... I think the x coordinate. You put the result on H, and then you read. And now you don't do anything. And I was putting A on B for use later, for some reason. But now I guess I saved the register and I don't need to do that. Now I'm putting A to H. What is A? It's the previous... I'm not sure. The thing is, I end up doing LDA, BC. Give it to me. Whatever B and C is, give it to me. I don't care. Just give me the value without any offsets. And I have saved a lot of... those are like 2 knob cycles, 3, 4... But I did a lot of changes before. It's getting crazier and crazier, man. Let's run this one. Let's try. Let's run the C version. The C version is that. We can even compile from outside now. Let's run it. This is the definite version so far. Although I have some other optimizations, but this is... Yeah. This is where I might have hit that. You see, yeah, 9 frames, 10 frames, 8, 10. I was hitting 10 to 12, so I must have done more. Yeah, that's the... This is where we're getting close. So I must have been doing more. I'm doing some. Yeah, there are some weird stuff. I was doing a shift right at some point by 1 in some of the values because of something that happened with the Julian number. It's hard to explain. There are some details. I was doing some additional shift right by 1. And I managed to find a way to not need it. But initially my values have exploded. More single knob cycles say. What the hell have I done here? If you have left, I don't blame you because this is taking long, but I can't help it. This is my style of videos, I realize. That must be some rearrangement with the register. So I was saving Z80 cycles. After I have... The bulk of the thing was the big... the C prototype to put numbers in 8-bit ranges. try to do no multiplication, everything in lookup tables. Then it was the subdivision. Then this kind of rearrangements of the data storage was very important to simplify things and save a lot of stuff. And then there were more micro optimization, more ideas, some significant, some less significant. I must have been saving some registers. I might be reusing, you know, when you finish the iteration, the next values are the previous, so you can store the next values in certain register that you have to not touch. I had to rearrange a lot so that they come normally. I'm not sure what I did here. I saved one upcycle there. I don't think that's the... No, you know what? Let's see how this... Did it improve anything? I must be doing some other tricks. There is one funny trick I do. I might want to show you. I must... Oh, and do you see there are some garbage now? I must have done something to go to 10 to 12 frames. This is very close. But I overflew some numbers. One reason, here in the previous change, I was not sure about precision. It's almost there. There are artifacts I could hide. I hide the artifacts at the end because that are the edges. So I do more crazy stuff. I change the escape value to be more... I must have saved more here. I don't do this shift right, which is 2 knob cycles. But that's it. So in the pre-calculations, I would shift left that value. I will enlarge that value because there was something that goes from the initial code. There was something, either precision or something with my numbers. And why enlarging the numbers would be better? Wouldn't it be now smaller? Something, you know, it becomes very unpredictable with the fractals when you feed the values to previous values. Something was happening, and in the very initial C code, I have to shift up to duplicate the value here. And see, I do the same for the Y one. And I found that, at least for the X one, I found a way to avoid the shifting, because later I have to shift right by 1 on the assembly algorithm later. So I pre-calculate some larger values here. I mean, that's going to just grow the escape value. I thought I could figure it out, but I did this because I realized if I do this, I will save some. And I realized later I might have more flexibility with some registers. I'm not sure. And okay, we are going to finish. This is a crazy, maybe unnecessary optimization. The escape table. No, the escape table, which is here, it was the table that will tell you previously it will have either a 0 or 1 to tell you if you give me this x and this y and I multiply, are they outside the escape value or the inside? So I don't need to do the power of 2 calculation or read from table. I can get an x and y very cleverly here with the offset, and it can tell me directly escape or not escape. And this is a silly, maybe it's unnecessary, because previously it's just 1 knob cycle. It's like, why, man, why? I would read, this is now, this will be the value, the final value from the escape table. It will be read on A. You will lower it with A to see if it's 0 or 1 and escape. So now I compare whatever is there with whatever A is. And it happens that A above okay, let's see. It might be the Y1 that is shifted right and added to E, which is, oh god, I don't remember. The thing is, it happens that now I recreated the table that is either a value that will not happen, 128, I found the value that will not happen, or Y1 shifted right 1 plus escape tab offset other. Okay, I'm going to show you. So that was a truth table initially, which was either 0 false or 1 true. And just to save one knob, so that's an even more needless optimization. But it didn't cost because it's the same table, same. I didn't fill memory with more data, so why not? So that it happens that in this algorithm, A comes with the thing that will either give, if you compare with, it will never be 128, but it will be the values I store at that position. It's hard to. So I avoided LDA, comma, parenthesis HL or A with a direct CPA, comma, HL, which is the same cycles LDA, comma, HL. So it was the thin micro optimizer, but with a bit crazy idea in a sense. And actually, we can see what I store now. Yeah, that's a really good form. I haven't. This junk pixel are overflow on the distance, and later I hide them. I erase them in some ways. And let's see now. The escape tab is at 8000. It will be just fine. It used to be zeros and ones. But what is it now? Here it's 80. It's actually the same address that you feed. 80, 81, 81. See, the 82 is the high byte of the address. Because it happens that you created this address, you fed it to A to add some offset and get it. And you see, maybe we can see. Add A, E. What is C? Ah, you know what is? Before, so everything, when you calculate the per pixel, everything is in the extended register. And those are prepared, D and D. So E is esc-tab of address. It's this address. Why this? Because it's in the middle, so that I add the y coordinate, negative, positive, and it goes up or down and selects the line. And then I add the x minus 32 to 31, and that wraps around as I add it. So it's such a crazy at this point. So I prepared this one. It happens that when I rendered the Julia, in this whole loop I am inside the extended register. I never switch back. And I never touch D, I never touch C. I put D on H, is the other table offset, the high byte. I put in. It's amazing that with so few 8-bit register I could fit everything so that there are minimal, register rearrangement, reading variables from memory. You read only what you need to read. You read from the lookup tables, and you write back. So that was the other thing. And it happens that when you construct the 8s, which is what you get, is the esctab address, it happens that that value also existed in A just before the compare. So you get it. It's like a mirror of the high byte of the address it's stored. And here, when it's not mirrored, this might be 4, this might be true, or the opposite. One might be escape, the other might compare that byte to its high address, the way it happens to be on A register on the accumulator, so that it escapes. Crazy, eh? And I do CPA, HL instead of LDA, HL or A. Also, I haven't said about that. Why do I do that later? That doesn't affect the flag, so I do it after. Those are, I have forgotten about that. Those are the values. Those are the byte values. Let me see if I can. I might not be able to find them anymore. Yeah, this is the fat pixels. Every byte is 2 pixels, and there are 2 pixels of color 1, 2 pixels of color 2, 2 pixels of color 3, and so on. So when you normally render the Julia, like if I put the release mode, the PC mode, you get the pixel from the iteration and it maps to the byte value for the 2 pixel. That was another micro optimization, that on the assembly code, since you know which iteration you escape, before you escape with red Z, you put the value of the byte directly. So there is no mapping of the iteration value 0, 1, 2, 3 with a lookup table on the fat pixel byte. It's directly the fat pixel byte inside that is fed before it escapes. And here, if it doesn't escape here, that's the final fat pixel. 3. It's not even there. No, it is here. I have some more values later. Okay. So that's the crazy one. Erase the junk version. I need to finish that. I feel like I need to finish that. So briefly, the way I erase a value, I have another table, but this is on the subdivision table. The 2x2 blocks, as some pixels at the end that they are not touched, I say these are, you will put black, you will put 0. It's the same color for the 4 pixel and 0. So it's a bit of cheat because I don't need to calculate some very few pixels at the edge. Yeah, those are the junk, man. Those are the junk stuff. Final version with the junk. 10 iterations are cool, but I stop. I added 2 more iterations. And usually, in the majority of it doesn't happen. So no junk. Those are 10 iterations. I had more colors added for the... yeah, if you want more iterations, you might need to do... no, that's it. Ah, hold it. I might don't do it for the C side, C version. I do it for here. I had to add more palette. Yeah, that's the final. 10 frames per second, 13 sometimes. You know, if it's top on the fat cycle or some other iteration, it goes 9, really. And that's the final one. And this is the palette I was using. I could have done better palettes. These are 10 iterations. And that's mostly it. And finally, much later, I migrated the project to a new CPC framework. And I wanted to... So I've worked a lot with that. I did some automations here. I'm sick of it. Oh, wow. Yeah, I was using increase L. Ah, that has nothing to do with it, Julia. I did some kind of data extractor. I was mostly preparing this to have some data and have different parts. And when you build, this is different parts. I was going to do some landscape shit or something else. It's not ready yet. And all of these are packed in a bigger binary. I made a tool for that, where the base framework would say, give me this with this index. It generates an index actually. But that's outside. Okay, that's outside of this video. I'm just excited about this demo framework. And then I scrapped all this demo framework. I didn't scrap. We decided to make the intro. And so I did more work to convert everything to assembly, even the initializations. And this is where I messed up my, if you see in the demo, this movement, I display the movement here. This is much better. You know, it goes into an ellipsoid, then it goes vertical, so you see more. It takes time till it repeats. But on the intro I released, it was repeating very early. Because I messed something on the conversion. And this final version, you have seen it in another video. I can press, do I have it? Space, okay. And finally, you can see that it is real time. Because I can do stuff. You can move around. And there will be some artifacts if you go too far. Obviously. It is real time. At some places it gets 9 frames per second. That's the worst you can get. Far away it goes 16 frames per second. It has the overflows, okay. But put it and move there and that's it. And that's the majority of the optimizations, I think. I'm sorry it took so long, but I guess that's the nature of my videos, especially for something that I have to explain everything. Okay, we started with pure C prototyping. We started with the original iteration with the multiplication, which I still have here, and ended up with, I have changed a lot in this file, ended up with something that use power of 2 tables multiplication tables x and y with offsetted addresses at this point. Escape table that gives you, you don't even do the power multiplication, you don't do that. It gives you the answer whether it's in or out. We ended up with something that will do, and let's put that. 2 by 2 subdivision, and then if the 4 pixels are the same, we'll skip going to finer detail, else it will go to finer detail and calculate the other 3 times the Julia. We ended up with something that was doing a lot more tricks. I started saving off Z80 code, and now look, one iteration, the first iteration says LTL, B and LDL, C, because B and C are coming from outside, is the X0 and Y0. But as it moves, it says LDB, L, LDH, D, because I happen to fit the X1 and Y1 that have to go to X0 and Y0 again for the recursion. So later it's the same. The first one is like this, later is the same. And you ended up with something that's more like this. The smallest iteration so far. This is one knob cycle, 2. We count in knob cycle on CPC, it's not the same as on Spectrum. And one knob cycle is 4 regular cycles. 2 knob cycles, 4, 6, 7, 8, 9, 11. The one auto modification there. 11, 13, 14. I think this is 2, even if it's a shift. 16, 17, 18. I think this is 2 or 3. I think 2. 20, 22. And that return, it's 3, I think. Whether it escapes or not. 25. 25 knob cycles or 100 regular cycles per iterations. And then you have the subdivision, so maybe half of them are happening. And the mirroring, of course, of the Julia, which was the most obvious. Amazing. Amazing that the final iteration is that. Take it. That's it. I made the iteration. What is this, man? Here you say LDA, BC. What is that? What? If you say that, and you say this is the iteration which started from that, you are like, okay, what your multiplication? Where are your multiplication? Okay, they are lookup tables, okay. Why is it so compact? Why is it so good? But look at the extreme marathon of optimization. In high level, in C, in minimizing values, in rearranging your data structures to overflow tables for the Z80 assembling. Again, high level, subdivision, low level, saving of Z80 cycles, improving the algorithm. It's crazy. Doesn't seem that I want to stop. Here is the code. So I did all this work in the C side, and I had to convert everything in assembly. Even things. So I was doing the heavy stuff here, but I was doing the initialization of the lookup tables, the skip edges, here I'm doing the movement, and I'm using some other Z80 sign multiply 8 by 16 that I shift left by 8 at the end, and I'm multiplying, I'm scaling. These values come from the signs. TAF plus 64 is cosine. because it's a 256 sine table. And those values, again, there are some scale values that are also moving by sines with different frequencies, and that's the timer. So I multiply this with that to make the more interesting movement, and I transferred this here in the final demo, and I didn't realize. I was pulling my hair. So I had to rewrite all these C functions painfully, all in assembly, if I wanted to make the intro and not a demo. And even in a demo it takes some space, but I guess with some compression in my demo system that loads each part separately. Actually extracts it from the high memory. It would be okay for a big demo based with partially in zip and partially in. But anyway, and somehow I missed it, and unfortunately I don't have the good movement. This is the movement of the original demo. See, it does this weird cycle, and it does this smaller cycle, and then look how it goes, 1, 2, and that's it. While the other one you have seen, and that's why it looks a bit repetitive. Although it's not that bad. This one, I don't show the, yeah, okay. Might not be the final. That was unfortunate. And here I want to show you something final, maybe. This is how cool it is. I have the iteration here. I have in this code, in the C side, I used to copy this iteration. I mean, they're not much. I don't know how many bytes. And because I was doing an intro, I wanted to save some bytes, and I have a generator which gets the iteration at some point, some other initialization code somewhere. I'm going to keep it short, and it will generate the iteration. That's how, when the demo started, the intro, you will see 1 iteration, 2 iteration, 4 iteration, and I would gradually upgrade. Now, it says 1, but I have disabled something in the script, so it's 10 really. So, if you run 10, and it would be 10 anyway because of the script, you get 10 iterations, which is the regular one. But you can go for 16, although the colors will be wrong. It will generate more code, as much space as it has, and you see it will go. Now the bytes are wrong, of course, because I need to do some tables for the graph, but it works. It will automatically generate the code with the iterations. And now it's 32, but the colors of course are wrong because I don't have the tables that point to the generated colors for the extra iteration. See, it goes slower. You can go 128 maybe, if there is space. This is a real fractal. This is a real fractal that could have, although it's unnecessary to have so many iterations because the detail. And see, when it goes close, it goes slow. Because the iterations go like crazy. And when it's far away, very few of the pixels have that amount of iterations. And where do I store the iterations? I don't remember. That's something with the script. Here is prepare render block and start iteration, and there might be some kind of copying. Final. I think it was here. Should have been here. Come on. Okay, I'll find it. It goes here. Render Julia Pixel Final. D800. And that's 20 episode. Oh, it might crash even. Let's see. See how bad now the D800. Ah, no, just do it here. Don't do it in the memory. And this is where I repeat the iteration. Goes 128 times. Oh, it might hit the... Okay. Might have already hit. No, E0 start the... That should have crashed. Or okay, I fed it wrong data. Because at T0... At T0... C, D, E starts the mult tab. Yeah, it's going to read some wrong data here with so many iterations. But it works. But it's not going to crash. Amazing, isn't it? I just want to revert it. Yeah. Amazing. Yeah, something. And that's it, guys. That was the big episode of... Sorry I couldn't help it, and maybe the nature of my videos are like that, especially for something that has so many details. You know, this is the big nature of the epic battle to optimize on all fronts with common sense ideas, crazy ideas, rearrangement of data structures in memory, high level optimization, reducing the mathematical range of numbers, doing subdivisions, doing everything in lookup tables, fitting them in weird ways, then saving of Z80 code, and doing a lot of other stuff. This is how you do it. This is how you approach something which is very rare. I just love the wallness of this effect. I think it's the best effect I ever coded on Amstrad CPC and Z80. And it could be improved. I have some ideas. Even to do it in other Z80 platforms, like the Sam Coupe. Maybe a higher pixel version. Maybe there are ways I can use those gap, even if I lose 1, 2, 3 knob cycles, but I gained a lot. What if it's 30 knob cycles and not 25? So there is a way to make the data a bit bigger and fit them in different ways to do a bigger, kinda slower but bigger and more impressive pixel resolution version of the effect. It never ends. The dream never ends. This is what fascinates me. So sometimes I'm tired of the design demo that shows you an effect for 5 seconds. I want the old, here is a screen. Even with, I should have added some interactive parts, but okay, I guess. And that's it, I need to go, guys. Bye, and see you in some other kind of video. Whether it's a big monstrosity like this or not. See you.